So I plan to still deliver this talk live at the conference, but I thought I would really quickly record a just in case version and stick it up on YouTube in case there are any technical difficulties. This is an activity that arose in my mind when planning for the possibility that all the courses that I taught this semester might be online. And I was coming up with some virtual lab activities for the students that could be done remotely. And a few of them were computer simulations. A lot of lab activities I do is computer simulations in my lab, but I had to come up with some that students would be able to do on their own, regardless of whether they had a PC or a Mac or a Chromebook. And so I decided to write some computer programs in Python using an IDE that can run on any browser. The IDE is called repl.it, repl.it is the website, and it has pretty much any computer language you can imagine available. I've used this IDE to teach C++ and Java both, and I've used it to teach myself Python, and I chose to write the programs for my courses this semester in Python, mostly as a way to force myself to get better at the language, which I only just started teaching myself about a year and a half ago. So the Replit IDE will run in any browser, and the students, rather than running a program that has some sort of graphical interface, are running a program where if they want to change something about the program, they actually have to get into the code and change the numbers and parameters themselves. The program is a relatively straightforward program that calculates the orbit of an object under a gravitational field. It computes the force from Newton's law of gravitation and then the acceleration and breaks it down into X and Y components and calculates the new horizontal and vertical velocity. And you can see that the program is what I might call aggressively commented. Every single line of the code has got a fairly detailed comment that explains what that line does. And the students are instructed to change particular lines of the code to accomplish certain things. The output of the program is not a live simulation. It is a static picture of the output of the orbit that results from the parameters that the simulation starts with. Since the orbit is plotted in discrete time steps, you can see the speeding up and slowing down of an object in the orbit from the spacing of the dots. And the program also spits out the parameters of the orbit. Once a full orbit is completed, it calculates the period and the semi-major and semi-minor axes and the eccentricity and the maximum and minimum speeds. And so that information is given to students as well. The activities are mostly just to try to create an orbit with particular characteristics. As far as the instructions the students are given, I recorded a demo video on Zoom of me running through the program and showing what needs to be changed and where you see the output and how to view the orbit that results. And I also give them a handout showing the various parts of the interface and what needs to be changed in order to accomplish the activities. Most of the activities simply ask the students to adjust either the initial tangential velocity or the initial position of the orbit or both in order to try to create an orbit that has particular characteristics. For example, the first thing there has to do is to try to reproduce the orbit of the Earth. If you start the exit at 1 AU away from the sun, what do you have to make V be in order to create an orbit that's approximately a circle? Suppose you wanted to send a spacecraft to Venus. Can you create an orbit that touches the Earth's orbit on one side and Venus on the opposite side? And do the same thing with Mars. What velocity would you have to use to send a spacecraft that starts at the Earth and meets with Mars on the opposite side of the sun? And then finally, just through trial and error, figuring out how fast you have to launch a spacecraft to launch it out of the solar system entirely. And the program actually gives a little warning when the distance of the spacecraft is such that it will leave the solar system and never come back. And so the students can just figure out what the minimum velocity is necessary to get something to achieve escape velocity through trial and error. Some other activities ask the students to change the initial position of the planet to match the average distance to Venus and Mars, and then to try to find the velocities that reproduce those orbits, the average orbital velocity of Venus, and then to compare that to the actual accepted value, to look that up on Wikipedia and see how close the value in the simulation is to the actual value. Of course, students could, if they were clever, actually look up that average orbital velocity first and then plug it into the program. But looking at the results, I don't think anybody actually did that. I think they actually all used trial and error as they were asked. More advanced students in the version of this lab that is for my calc-based physics course, students are asked to do things like figure out if you were going to change the strength of gravity in this universe by increasing Newton's gravitational constant. What line of the program would you do that? If you were going to change the Newton's law of gravitation from an inverse square law into an inverse cube law, what line of the program would you change? So the idea is getting the students comfortable with looking at computer code, reading the comments, figuring out what the parts do, and then tinkering with things and seeing what happens. Finally, asking students what would happen if you changed big M, the mass of the sun, what would happen if you changed little m, the mass of the orbiting object, and then to actually do that and to see what happens. As far as the results go, I gave this assignment to my astronomy class a few weeks ago, and most of the students in an introductory astronomy class seemed perfectly capable of digging into the code and tinkering with the parameters and getting answers for the orbital speeds that were correct, that gave the orbits that were asked for. So this gives me confidence that should I decide to do a lab like this in the future, it is not something that will frighten off all the students having to dig around in the code and to mess around with stuff. For the students in my calc-based course for physics majors, that's Physics 202, most of them were able to figure out where in the program to make the required changes and to show that the changes, when they made them, matched their expectations. For example, figuring out the syntax that would be necessary to change the 1 over r squared law to 1 over r cubed law, figuring out what would happen to an orbit if I changed Newton's gravitational constant to something larger, and so on. Some of the questions required the students to understand some physics. For example, the question that asks what would happen if you change little m, which represents the mass of the orbiting body, which you probably all know it cancels out when you write Newton's law of gravitation, that F equals ma, little m cancels out. The orbit does not depend on the mass of the little object. Some students got that right and predicted it correctly. Some students predicted it incorrectly and weren't able to connect this fact, which we definitely talked about in class a few times, to the operation of the program. And so I thought that was actually a really, really nice way of assessing whether they really kind of understood the impact of the difference between changing the mass of the central object and the mass of the orbiting object. So that actually turned out to be a nice little question. As far as the learning outcomes from this, I didn't intend students to learn how to code. I didn't intend students to learn anything about Python syntax specifically, but what I wanted to kind of confirm for myself that it is viable to have students dig into some computer code, change some lines around, and to look at what happens and to connect that understanding of what happens in the code to what happens in the physics. So in that regard, I thought it was a successful experiment, and I plan to do it again next semester, especially if we are still doing courses partly online. I know my astronomy course this semester has been completely online, so all of our labs have been virtual. My astronomy class, or my physics class for majors, is a hybrid course. Half my students are in person, the other half are online. So the need for virtual type labs is still probably going to be necessary next semester as well. And this kind of approach is one that I plan to continue. So feel free to ask questions in the YouTube video. I will post a link to the code in the description of the YouTube video if you want to go to repl.it and check out my code, which is kind of clunky but gets the job done. If you have any questions, you can shoot me an email at dmorgan@rbc.edu. Thanks.